So we're talking about how to solve a basic trig equation. We are going to not use a calculator or a graph when we're actually doing it, but I did want to explain why there's an infinite number of solutions and how we're going to express those solutions in a way that makes sense. And so the first thing is, if we want to try to figure out, the equation we were looking at on the other slide was 2 times sine of x minus 1 equals 0. So one way to solve that is to look at the graph of 2 sine of x minus 1. Put that equation in decimals, and I'll show you that graph. We've done enough with graphing where you guys can probably be convinced that this is a sine graph that was moved down 1. Its amplitude is 2. And if the equation we're solving is, hey, when does this equal 0? We're trying to figure out which x's can I plug in to get 0 to pop out. And anytime we're having 0 pop out of a function and we have the graph, that's like saying, what are the x-intercepts? So I can look at this graph and we can see all these different x-intercepts here. Clearly there's infinitely many. It's not going to be all real numbers, but if zooming out, this pattern's going to go on forever and there will literally be an infinite number of solutions. How are we going to express every single possible solution? I can't write all real numbers, but there's got to be some way to write all these infinite number of solutions without, doing something like that. So here's what we have. Without going into too many details, I can have this Desmos graph all these x-intercepts for me. So as I click on these two buttons, I hope you guys can see there's a bunch of purple points and green points. And you might be wondering, why is Mr. Defsick breaking these up into two separate sets? Why is he making green and why is he making purple? Well, here is the reason, my little friends. Let's zoom in on just these green points for a second. All of these green points happen to be exactly 2 pi apart, right? If you look at this more carefully, there's a green point here at negative 11 pi over 6. There's a green point over here at pi over 6, and one over here at 18 pi over 6. I also want to point out all these x-intercepts have something in common, and that is that they're the x-intercept when the sine graph went from below to above, from below the x-axis to above the x-axis. So they have that in common, and they're all exactly 2 pi, or 1 full rotation, apart. If you don't know what I mean by 1 full rotation, I will clarify that when I give the official notes, but you might remember earlier in the year we talked about how 2 pi was a full rotation. That's going to come into play today. It's coming into play right here. If I take negative 11 pi over 6 and I add 2 pi, I'm going to get pi over 6. If I add another 2 pi, I'm going to get 13 pi over 6. And the next green dot, that would be from when the graph went from below to above, would be an additional 2 pi away from this point. The second set of points, the purple ones, are also, they have this in common. They're all the zeros that happen when the graph went from above to below. And they are also all 2 pi apart. They're a full rotation apart. If I take negative 7 pi over 6 and I add 2 pi, I'm at 5 pi over 6. If I take 5 pi over 6 and I add a full rotation, I'm at 17 pi over 6. So I want you to keep this in mind. It's like there's two different starting points, the green and the purple, two different starting points, and all other ones are going to be one full rotation away. So now we're ready to give official notes on how to do this without a graphing calculator. We're going to look at a way to express the infinite number of solutions, and it's going to be like a great chance for your brain to get really strong. It's going to be so fun. You're going to like it. The next video, I think, is the last one. We'll just do a few examples and an assignment. It's going to be great.